We're looking at a massive leap here, how we've evolved from those standard, everyday image generators into unified world models that actually understand sight, sound, and motion, all through one incredibly elegant framework. Flow matching and rectified flows. This is all about setting our continuous time foundation.
So, to put this simply, think about how older AI models worked. They tried to instantly guess what an image should look like from random, static noise. Rectified flows do something entirely different. They learn a precise, continuous trajectory, what we call a velocity field, that's required to literally transport that noise into actual data. The crucial point here is that by learning these straight paths over continuous time, flow matching completely bypasses a lot of the headache-inducing optimization challenges of older systems, like generative adversarial networks. It's a mathematically smoother and just vastly more stable way to generate highly complex stuff.
Moving to Section 2, the representation bottleneck, or the structural deficit of standard flow models.
I really want you to think about this question for a second. If a model is optimizing to reconstruct just tiny local patches or individual pixels, how on earth can it ever develop a global, structured understanding of what it's actually building? It's like trying to put together a 1,000-piece puzzle by only looking at one piece at a time. The reality is, standard denoising objectives are inherently local. They're great at cleaning up static pixel by pixel, but they give the network absolutely zero incentive to understand the actual semantic meaning of the whole object. It doesn't know it's building a dog. It just knows how to generate brown fur textures.
And historically, this gave researchers a massive headache. You basically had two choices. Option A, stick with standard flow models, which generate great pixels but suffer from total local blindness. Or option B, try to inject some intelligence using something called external alignment, or REPA. This meant forcing your generator to align with frozen, already trained models like Dino V2 or CLIP. But the catch? It creates a severe architectural bottleneck. Those frozen spaces are super rigid. They don't align perfectly with the continuous generative trajectory. And worse, they create massive modality mismatches. I mean, imagine trying to apply a vision model to an audio file or a robotic actions. It just doesn't work.
But the data we're looking at here gives us undeniable proof of a totally new way forward. Notice the Frechet inception distance, the FID metric on this chart. By completely ditching those external models, this new self-flow framework converges 2.8 times faster than external alignment methods like REPA. That's almost 3 times as fast. And even better, while REPA eventually just plateaus, self-flow just keeps improving its generation quality. It literally removes the bottleneck entirely.
So how do they pull this off? That brings us to Section 3, Dual-Timestep Scheduling Explained. Let's look at the math.
Instead of just slapping a single, uniform level of noise onto an entire image during training, Self-Flow uses these 3 very specific steps. First, the scheduler grabs 2 completely independent noise time steps. We'll call them T and S. Next, it drops a random binary mask right over the data, usually covering about 25% of the tokens. Finally, it corrupts the input heterogeneously based on that mask. Think of it kind of like a teacher testing a student by partially erasing a chalkboard. The model is forced to deal with this intentional information asymmetry. This breakdown shows exactly how that works in practice. The unmasked tokens get hit with the noisier time step T. They are heavily corrupted. Meanwhile, the masked tokens get the cleaner time step S, which gives the model a low noise context. Guys, this heterogeneous noise assignment is just pure genius. It literally forces the network to stop obsessing over local pixels. To figure out the heavily corrupted structures, it has to look at the cleaner context tokens. It has to understand the global picture just to fill in the blanks.
Which leads us perfectly into Section 4, inside the self-flow architecture, where representation and generation finally become one.
Okay, here is where the absolute magic happens. The system maintains 2 networks running at the same time, kind of like a master and an apprentice. The student network gets trained on that messy, heterogeneously noised input we just talked about. Meanwhile, an exponential moving average teacher network gets to look at a much cleaner version of that exact same data. Then, the system evaluates the token-wise cosine distance. Basically, it's grading how perfectly the student's understanding matches the teacher's understanding. This is a self-distillation process, flowing from the deep teacher at layer 20 down to the shallow student at layer 8. So, the student model is forced to predict the high-level semantic features of the teacher while simultaneously predicting the velocity field to actually generate the image.
And the results? They speak for themselves. Notice the incredible structural coherence of the parrot's feathers in the self-flow generation on the right. Compare that to the vanilla flow matching on the left, which honestly just looks kind of jumbled and messy. Because self-flow forces the model to learn global semantics internally, the model actually understands how feathers are supposed to overlap and connect in the real world.
And we see the exact same breakthrough when we move to video. Look at these frames of a woman doing push-ups. With standard flow models, it totally fails to grasp the temporal consistency and structural geometry of a human body moving through space. Limbs might randomly morph or clip through the floor, but the self-flow framework corrects this entirely. It understands the persistent physical structure of a person across time, all because those generation and representation feedback loops are constantly reinforcing each other.
All right, Section 5, Flux 3 implementation details. Let's look at how this scales into a multimodal powerhouse.
95%. That is a staggering number. 95% of Flux 3's training compute is consumed solely by video prediction. Meanwhile, audio takes up less than 0.5% of the tokens. Now, you might be wondering, why such a massive disparity? It's because video forces the model to learn the laws of physics. It has to learn about contact, motion, weight, cause and effect. If it gets any of those wrong, the visual output looks broken. But once it truly learns visual world dynamics, mapping audio onto those events is actually a remarkably simple task.
So when we pop the hood and look at the Flux 3 specs, we're looking at a unified multimodal model built on a scalable interpolant transformer backbone. And it's jointly trained across image, video, audio, and get this, even robot action data. Amazingly, the Flux Mimic robot policy can execute in under 80 milliseconds on a single consumer-grade RTX 5090 GPU. The most crucial takeaway here is that this is one single set of weights. It treats every single modality as a mutual constraint. That means the generated sound absolutely has to match the visual impact, and the physical motion of the robot has to obey the mass it learned from watching video.
And honestly, the output capabilities are staggering. Being able to generate massive, continuous 20-second clips natively, completely synced with audio, is a total game changer. It fundamentally separates Flux 3 from earlier image-only models like Flux 2. Because it learned these modalities together from the ground up, the audio isn't just awkwardly tacked on at the end. It's generated jointly as a singular projection of an underlying physical reality.
Finally, let's hit Section 6, Limitations and Future Horizons. Where exactly is the frontier of multimodal world models? Well, we do currently face a very specific mathematical hurdle called the low-noise pathology. Basically, as the generative process gets super close to the final clean data, tiny little perturbations cause massive chaotic spikes in the velocity target. Think of it like trying to fix a microscopic scratch on a priceless masterpiece, but you accidentally smudge the whole painting. The model ends up wasting way too much capacity modeling noise instead of extracting high-level semantics. So resolving this, using hybrid training protocols like local contrast to flow, which replaces direct velocity regression with feature alignment when the noise is low, is going to be absolutely essential for pushing flow models to the next level.